Okay, let's talk about waves. So here's a picture of an ocean wave. So we have two basic types. Really, we have three different kinds of waves that can exist. Mechanical waves that are waves that require a medium, something is moving, but the stuff that's moving is not moving along the wave. In the sense that, say, we have a water wave. It's not the water that's moving from one place to another. It's energy that's moving from one place to another. While the water just, say, oscillates up and down, energy will move left and right. Sound waves, seismic waves, these are all mechanical waves. These require a medium. Then we have electromagnetic waves that do not require a medium. It's space itself that's waving up and down or left and right. Like light. In fact, all electromagnetic waves are just light. There are also matter waves where what's moving is literally the matter that's moving along the wave. In mechanical waves, energy is being transferred. In matter waves, actual stuff is being transferred. But we won't study matter waves in this class, so we don't need to worry about that. Okay, the two different kinds of waves or waves can travel. Now, this is a different topic than types of waves. Here, we can have transverse and longitudinal waves. Transverse waves, the stuff is moving up and down while the energy is moving left or right. In longitudinal waves, the stuff is moving left and right, and the energy is moving left and right. In transverse waves, the material itself is moving perpendicular to the direction of propagation. In longitudinal waves, we're moving parallel to the direction of propagation. So, water waves can be a combination of both of these, but when you think of a water wave, waves going up and down, like say this bird here on a wave. So the bird will be oscillating up and down while the energy is transferred left and right. So we would see a wave coming at us. If we were over here, we'd see a wave coming at us. But the water's not actually moving toward us, just the energy. The wave is moving while the water is bouncing up and down. So the direction of the water moving is perpendicular to the direction the wave is moving in. Longitudinal waves, on the other hand, stuff is moving back and forth in the same direction the wave is moving. These are pressure waves. So this girl's got this slinky and she's squishing and compressing and stretching, compressing and stretching. So these little compression zones would be moving along the wave. You're down here, you see high pressure zones and low pressure zones coming at you. And the slinky is oscillating left and right. The wave is moving left and right. In longitudinal waves, the oscillations are in the same direction or parallel to the direction the wave is moving. Sound is a longitudinal wave. It's a pressure wave. The air molecules are bouncing back and forth instead of up and down. Okay, so a typical transverse wave would have this kind of form here. We call the distance from one crest, that's the top of the wave, to the next, the wavelength, that's the distance in space. These tops are called crests, the bottoms are called troughs. The distance from one point to the next is called the wavelength. The height, if we were out on the ocean and we're watching the waves go up and down, then the height of the wave is not the total distance from top to bottom. The height of the wave is the height above a flat, calm ocean. And we call this the amplitude. So the entire wave is 2 amplitudes tall. That's how far the bird moves here as he goes up and down. As he goes from the midline to the top, that's 1 amplitude. The wave itself is moving perpendicular to that. This is a transverse wave, and it's moving at speed v. And remember, all that's being transferred in a transverse wave is energy. Energy is being moved to the right. The bird is being moved up and down. Okay, so you definitely want to write all these in your notes. Lambda here is the wavelength that's measured in meters. That's the distance from one crest to the next. A is the amplitude, also measured in meters. V is the wave speed, the speed at which energy is being transferred. And that's, of course, it's a speed. It's meters per second. Okay, so we have a picture here. We've got this oscillator bouncing up and down, and it's creating these waves. So we've let this go until it's created one complete wave there. We call that time it takes the period. So T here, we'll write this down in a minute, stands for the period. I've let this thing create one complete wave. We call that 1 period. The energy is being transferred to the right. These individual points, though, are moving up and down. So let's watch this dot here, over here at, let's call this x equals 0. This dot, at this moment, right now, is here at the midline at y equals 0. It moves up, comes back down to the midline, moves down to the bottom, and so forth. So this point here is moving up and down. The time it takes to go through one complete oscillation from here, it goes all the way to the top, back down to the middle, all the way to the bottom, and then back to the middle. That's one complete oscillation there. We call that the period. That's the time it takes. So that's from time equals, we've already done 1 period here to 2 periods. That full time that we're looking at here is 1 complete period. So period is the distance in time that it takes any spot to go through a complete cycle. We could measure here on this guy. He's at the top. He's in the middle. He's all the way at the bottom. And now he's back at the top again. That little purple point there went through 1 complete cycle. That's a period. Period is measured in seconds. But this wave we're looking at here is 2-dimensional. It's changing in space and it's changing in time. So if we were to just take a snapshot, say look at this one freeze frame here, everybody's moving, but we took a snapshot and we're just looking at this frozen moment in time. The distance from one crest to the next is what we call the wavelength. This distance here from midline to the top is the amplitude. So T is the period. That's the time it takes to go through a complete oscillation. If we flip the period over, 1 over the period, we call that the frequency. That's the number of oscillations per second. So if this thing is oscillating really fast, it might have a high frequency. So cycles per second. We call those hertz. And then the wave speed is how quickly, if we're watching here, this crest, see I'm watching this crest move to the right. If I'm just traveling along here. How quickly is that crest moving to the right? We call that the wave speed. That's how quickly energy is being transferred. If you see a wave coming at you, that's what you're seeing. How quickly is that wave coming at you? And that's in meters per second. So that's just lambda meters times frequency, which was 1 over seconds, or hertz, or meters divided by seconds. Wavelength divided by period. Okay, now we can have a lot of different kinds of waves. I don't want you to get the idea that all waves are sinusoidal in nature. Not all waves will look like a sine curve here, like this does. But those are some of the easiest to model. So let's assume we do have a wave that looks like this, that looks like a sine or a cosine. Then our general form would be one of these two. And these are almost interchangeable. It really doesn't matter whether we use a sine or a cosine. The only thing that changes there is our starting point. Then our formula will say look like this. Now you got to think back to when you took trigonometry. You learned how to find the period of a sine wave. You learned how to find the amplitude, the vertical shift, the phase shift, all that stuff. And you learned that period was 2 pi over b. 2 pi over the thing in front of x. Okay, but now we have a two-dimensional function. My function y, the height of the wave, doesn't just depend on time, it depends on my location and my time. So we have two different kind of versions of period here. We have our distance in space and our distance in time to go through a complete oscillation. So if we write a function that looks like this, then we call this guy in front of the x here, k, we call that the wave number, and that's related to our distance in space, because we're multiplying by x there. Our wavelength is 2 pi over k. That's the distance between one crest and the next. If we take a snapshot of the ocean and we measure the distance physically from one crest to the next, that's our wavelength. Then we have this guy in front of the t here. That's our angular frequency, omega, and the period is 2 pi over omega. That's our distance in time. That's how long it takes if we're watching the bird go up and down. If this thing is oscillating, the bird is going up and down. The time it takes to go all the way down and all the way back up is the period. The distance from one crest to the next is the wavelength. The time is the period. Now this thing's moving. We could also measure the period because this wave's going to be changing. This crest is going to be moving over here. The time it takes this crest to move over here is the same time it takes the bird to go up and down. That's our period. So we can look at the same picture again. So here, if we look at this snapshot right here at this moment, the distance from this crest to the next is the wavelength. That's a length that's measured in meters. On the other hand, if I just watch one single spot, I just watch this spot go down and back up, the time it takes to go through a complete cycle all the way down and all the way up is the period. Okay, so we have some function, y. Remember, that's what we're measuring, the height. That's why we have a y there. We're measuring the height at position x and time t. And we're assuming, for this example here, assume that goes like a sine function. This guy here, this phi here, is called the phase shift. And all that does is, instead of starting at 0, maybe we want to start at a different point on our sine curve. So we don't have to stress about that phi there. All that does is shift our curve over. What if I wanted to measure how quickly the bird is moving up and down? So this v here, that's the wave speed. That's how quickly the wave energy is moving left and right. I want to measure something different. How quickly the bird goes up and down. So that's not v that we have here. That's the wave speed there. What we want is v in the y direction. So we call that vy. That's how quickly an individual spot on the wave is moving up and down, not left and right. Well, that is, it's a velocity. It's the derivative with respect to time. But because we have a function here of two variables, we're going to have to take a partial derivative. So we're taking y's partial derivative with respect to time. That means everything else is treated as a constant. We just take the derivative with respect to t, and we treat x just like a constant. So the derivative of sine of anything is cosine times the derivative of the inside. It's just a chain rule. Derivative of kx, as far as t is concerned, is 0. Because we're taking the derivative only with respect to time. The derivative of negative omega t would be negative omega. And of course, the derivative of this phase shift here is just 0 because that's just a constant. So here is our formula for Vy. That's how quickly the wave is moving up and down, not the wave speed. That's completely different from wave speed. And notice it goes like a cosine, and it has a max of this amount right here, A omega. This whole derivation here should remind you of all the stuff you did with mass on a spring. It's very similar. And then, of course, we could take the acceleration or find the acceleration in the y direction. So that's just the second derivative of position or derivative of velocity with respect to time. So we take another derivative of this guy with respect to time. It's a partial derivative. And we get this formula. And then the maximum, remember sine has a maximum of 1, so our maximum acceleration will be A omega squared. Okay, and then we're not going to do much at all with the linear wave equation. But this sinusoidal wave here we're studying does in fact satisfy something called the linear wave equation, which looks like this. Okay, we don't even need to go through the whole thing. This will become important when we get to electromagnetic waves. Electromagnetic waves satisfy the wave equation, and it will just pop out here that we get a 1 over v squared, and from that we can derive the speed of light. This is where the speed of light comes from, is from the wave equation. It'll just pop up right here when we look at electromagnetic waves.